Good morning, good evening, good afternoon, everyone. Thank you very much for joining this webinar. My name is Anders Winkler. I am here with my colleague and co-host, Stephen Ribeiro-Aye. And today is a very special day. For one, it's a very exciting topic. And on the other hand, Stephen and I are actually for the first time, well, not the first time, but for one of the rare occasions, we are sitting in the same office. So we are very excited to talk to you about this subject. The topic of today's webinar is thermomechanical methods for additive manufacturing process simulations. Or I should actually be correct and say it should be award-winning thermomechanical methods for additive manufacturing process simulations. It's usually not considered good manners to brag about yourself when you do good stuff, but in this case, I have to say we just can't avoid it. Because a lot of the times we get questions from people we meet and how accurate our simulations are, have they been validated and so on. And we're actually very proud to announce that the solution has been validated by NIST. This is the National Institute of Standards and Technology in North America, where through a collaboration with TWI, the Welding Institute, we jointly submitted a blind prediction. It was later on announced by NIST that we had won the first place in best modeling results predicting the residual stresses in the benchmark in 2018. Most importantly, this is a blind prediction, which is then being compared to state-of-the-art physical measurements by NIST. And we believe this is a pretty good answer and an unbiased answer for the accuracy and validation, particularly as it is pertaining to elastic strains. But there's actually more in the pipeline, because in 2019, that's one part of the whole additive manufacturing puzzle. But we also were very proud to be the winning team in the 2019 Sendia Labs Challenge. This is what they term the Topology Optimization Roundtable Challenge. And basically the challenge was to use topology optimization in the design of a component for a Formula One race car. And whoever came up with the most effective design would be declared the winner. Now this was based on a couple of criteria that you had to minimize the mass and you had to make 3 different part versions, additive, cast, milled, and use 3 different materials, so aluminum, titanium, and steel. And basically, if we boil it down to a single thing, then the matter of fact that the duration using our solution was less than 1 day was, I would say, the chief convincing factor for the committee. So very happy to kick this off with 2 awards to the solution. Now, it's always fun to talk about history. I did this in the last webinar when Stephen and I were talking about the eigenstrain method. And this is I'm not going to dwell too long on this, but what I want to say is that we have been doing additive manufacturing for longer than, well, a lot of people really think. Because this first started back in 2014 with the very first AM simulation that was based on Abacus model change technology. And we honed this back and forth until in 2017, we released the first version of the end-to-end additive manufacturing solution, which we also refer to as Print to Perform, and which you have probably noticed in both social media and our webinars earlier this year. And what I would just like to say is that as of this year and moving forward, we are focusing on increasing the customization, because effectively you can say that every 3 or 4, maybe 5 months, there is a new additive manufacturing process coming out. And there's no way that anyone can keep up providing ready-to-go templates for these. It's simply not possible. So what we are simply doing is increasing the customization capabilities to be able to cover really any process. And this is where we focus on the simulation ecosystem integration, or in simple language, getting more input and getting even closer to our users who have started to adopt and coming back with valuable feedback on what it is that we do for additive manufacturing. So I did say that we have something which we call a fully fledged solution. And this is what we mean when we say full coverage. We actually speak about not just being able to go in and do a couple of local parts for additive manufacturing, but all the way from design up until the actual validation, let's say durability or a static fracture case, to actually putting a successful part out in the end of this chain. That's basically what we propose. And this is no dream, this is not a vision. It's just something we can offer with technology that's already been vetted, validated, battle-proven. If you have used any of our standalone or any of our legacy technologies in the past, you will know that this is nothing to be contested. But we're going to be talking about this more in detail, specifically on the thermomechanical bits, so I will simply move on to talking a little bit about challenges. The fact is, when you want to go from having powder in your hand that is going into the 3D printing machine to actually getting working parts out in the end, there are two ends, or two players on a big field, you might say. There is essentially the team design and there's the team field. And design are basically those people who dream up all the new and interesting and organic and fun geometries, and they're being presented with a lot of challenges, which they solve in the best way possible with the tools available to them. But the same goes for the people in the field who effectively have to more or less take the stuff that is being made for a test drive and tell the design team whether or not it actually works. Now, the classical way of doing this is by, well, using the silo approach, you might say. And the problem is that getting something from a concept stadium to an actual prototype is a process of going from weeks to months. It can take a tremendously long time because we're shifting information in a very inefficient way. So the question is really, well, if we want to reduce this, and that's what we have to do because it's a novel piece of technology, or, well, it's an old technique, additive manufacturing, but it's a novel piece of technology. We want to change this so that we're not talking weeks to months, but rather days to weeks. When you say, okay, that's a good idea, but generally this is the situation you're going to be faced with. A lot of concerned, frustrated, and simply confused faces in your workforce. So the question is, how do you bring the skepticism or the discrepancies of these two teams together and make it dynamic, make it completely collaborative? This is where we bring in what we call the end-to-end solution for additive manufacturing simulation. And effectively, this is based on 4 different components or 4 different pillars. It begins with the so-called function-driven generative designer. You will see some bits of that today, but not much because our focus is on a different topic. The second part is where you go through the step of actually preparing whatever it is that it's supposed to be built in the additive manufacturing programmer step. The third, and that's where we're going to be focusing our activity today, is the additive manufacturing researcher, which goes into deep simulation, tries to deeply and in a very detailed fashion understand exactly what goes on in the printing process. And to close everything off, well, you can consider it a small component, but it is certainly not an irrelevant component. And that's the reverse shape optimizer. This is the tool that can be used to close the gap between the as designed and the as built component. So it's absolutely crucial. We will touch upon it in a little bit, but not in detail. So with fair warning in place, I would like to proceed to the next section, which is simply to talk a little bit about the print to perform features. And rather than actually saying something along the lines of what each of these are, I'm not going to read features to you. And it's not the point. We're going to explore particularly the box that is labeled predict. But what we mean by this is effectively that in the corner of create, this is where the organic, out-of-this-world designs reside. And this is where the generic creativity, the whole imaginatory stuff goes on. In the prepare side, that's basically real-world manufacturing in a virtual environment so that you don't use up valuable machine time and cost on the production line, but actually you do it up front. The third component, or rather the third bucket, if you will, predict. This is the no-nonsense simulation of the printing process and a whole lot more, as you will see. We will address a lot of these things in detail, and we hope that's going to satisfy your appetite today. But finally, we end up with compute, which, as I was saying, the smallest puzzle piece that makes everything comes together, and that's to close the gap between as designed and as printed. Now, I have deliberately gone through the introduction a little bit quickly. If you have any questions to it, please save them until the end. And I'm now going to pass on to Stephen, who is going to take you through a couple of steps and then go into exquisite detail. Stephen, all yours.
Thanks, Anders. That was a very nice introduction, and let's have a look at some of the details we've been talking. So, of the 4 pillars we talked about, the first is the design pillar, and that's something that I would almost call a known concept, the role which you have the functional generative designer, which allows you to design parts in a new and novel way. It's commonly called bionic design, or technology is topology optimization, which will give us designs which may or may not be printable using additive manufacturing. And at this stage, we have the design created as we have it here. So then the next step then would be to look at manufacturing the product. So we're shifting the app, staying in the same environment, now shifting the app to the process planning, preparation. The design exists, and now we are looking at things like arranging the parts in the build tray where they should be, deciding which machine to use for printing, and since we are using a laser additive process here, we decide which kind of scan path, what laser power, what laser path we want to use. That is part of the process planning and preparation. With the information in place, with the support structures generated and everything, we are ready to print the part, or, and that's something that I think is very important, to simulate printing of the machine. So the concept that we're using here is pretty much similar to the paper printer you may have in your office. When you buy a new printer to print your reports, you normally run a setup configuration on your computer so that your computer knows how to talk to the printer. You run a printer installation from disk or a floppy back in the days, whatever. And the same concept applies to what we call for the virtual machine. So within our software, we have a virtual representation of your physical printer, like this Renishaw machine shown here as an example, with all the kinematics, the technology parameters, the build parameters that are available in the machine, and you're able to program that machine online using our software and sending that information in machine code right to your physical printer. And I think that's the important thing when we talk about digital continuity, we use the exactly same information to actually print the part in the simulation. So for example, shown here, for a rather complicated structure like this lattice, we do generate the print path, the laser scan path, and we use that information as an input for our thermomechanical simulation. So let's have a look at this simulation. That's the virtual printing process that we're looking at here. So in this virtual printing process, what we want to do is we want to incorporate the information from the print setup. We have the geometry, we know the material data, thermomechanical material data that is, of course. And what we do is we do two-stage simulation. First stage is the pure thermal simulation. We take into account the laser path that we just derived, put that information in our simulation, and see how the temperature field evolves over time. With this information, we can run the structural simulation, which will give us the information about the possible part deformation, about stresses, and things maybe not going as we want it to be in the print process, predictably. How does that work? And at this point, I want to go into some of the technology details that we have created, making the whole simulation possible. Oftentimes, when we present our thermomechanical approach, we are met with skepticism. People telling us, oh, this is going to take years, light years, or ages, or eons, or whatever. It's technically impossible to do that because they assume we are forced to use elements at a micromillimeter level size and simulations that take forever. Now, we wouldn't present our technology if that was the case. If it would take forever, if it would take all the computers that we have available on Earth, if that was the case. So what we do, we have two tools that allow us to do this thermomechanical simulation in very, very competitive time, giving very, very good results, as Anders already said, with the examples from the NIST award and the other awards that we got for this simulation. First thing that we have here is the Mesh Intersection Toolkit. This Mesh Intersection Toolkit allows us to map the information that we have gathered in the process data, such as the event series for space and time, showing us the position and the path of the laser during the simulation, and map that onto a real-sized mesh, allowing us to run real-sized parts. So we're not into extremely fine, extremely small meshes for part-level analysis. We have different ways of describing these events that happen in time and space. That include things like the power rating for laser, one laser, multiple lasers, whatever you like, mass flow rates for deposition processes, recoding processes, meaning activating elements, build changes, adding or removing elements, and so on. And this tool allows us to do this kind of simulation in reasonable time. The second pillar that we have for this kind of processes is the progressive element activation. So when you think about adding elements to a simulation model, or maybe removing elements at a later stage, let's look at adding elements. The common perceived process is that we add one element or more elements at a time in multiple steps in the analysis, forcing us to have hundreds, thousands, or maybe millions of analysis steps and adding elements one by one. That indeed is a costly procedure, and no, that is not the way we're doing things, because it would be too costly. We have a technology called progressive element activation that we're utilizing here. So we are activating full-size elements, regular-sized elements, whatever size you feel comfortable with, and we're only activating that portion of the element that corresponds to the current print height. Everything else in this element is not active, it's not taking part in the simulation, and it's not wasting our time and resources. This way, we're able to progressively activate elements, simulate the build process accurately, where accurately means things like taking into account free surfaces during the build, where we apply radiation and convection only to those surfaces which are currently existing and currently exposed. As soon as we add a new layer of elements to the model, as shown here on the right-hand side, there's no radiation anymore on that surface because those elements are covered. And this allows us to do a precise handling of the heating events, activation events, and whatever, allowing us to do this simulation with very high fidelity and at a very, very competitive speed. There are other technologies. I'm just showing this as a glimpse of what is available. We do have and offer the eigenstrain or inherent strain method, which is a purely mechanical analysis disregarding thermal effects. But today, we want to look at the thermomechanical simulation and see some of the features that are only available in the thermomechanical approach. So, when we talk about sequential thermomechanical analysis, as said, what we do is we first do a thermal analysis giving us a thermal field which changes in time and space. Can run multiple objects on the build tray with whatever laser path that we designed, print that, and then go into further steps such as removing the part from the build tray, or cutting the part, as you see on the right-hand slide here with the wire ADM, where it doesn't make a difference how the part is printed, how the part is being cut, yielding different results. When we do this kind of analysis, it's commonly perceived that we need to do heat treatment to do a stress relief analysis. That too makes sense when we do this kind of analysis. And if you look closely, you recognize that we did not use any simplification in terms of the elements. So we're not using voxel elements, large size elements, which cover the detailed feature of the part. We're using in this case, we can use shell elements or we can use TET elements to accurately represent the shape of the part based on the CAD geometry. And that allows us to do this heat treatment and actually see in detail which part of which region of our part is being heated and how the heat dissipates into the structure and see what is happening. Maybe we'll see deformation of the part during heat treatment, which is not wanted. On the same level, this is for post-processing, is of course the machining operation that we can do on the part. Oftentimes we will modify the geometry slightly to make it printable, and we need to do a post-processing operation. That post-processing operation can be quite expensive, and it is advisable to simulate that beforehand to see whether the fancy support structures that we just generated are actually in a position where we can remove them from the part without destroying it. In-service loading. we're talking about print to perform. Print to perform as in we're not happy with just being able to simulate the print process. That's not what we want to do. Simulate the print process in essential is nothing more than the birth of the part. Maybe more complicated, maybe a cesarean section as compared to simply milling part, but just simulating the print is not enough. We want to talk about print to perform. We want to see how that part that we just printed performs in service loading. So on the basis of the residual stresses that may develop during the print, and some of these residual stresses may still be present and affect the performance of a part after heat treatment. They're not going to vanish just like from a wizard, disappear. They affect the service performance of a part. Durability, as shown here on the side, is affected. And the stress distribution, the residual stress distribution, depends heavily on the positioning of the parts on the build tray. It depends on the use of the support structures, the temperature management, and things like the laser path, because that affects the stress field. And the stress field in turn affects the service life of our part. So it's things like that we need to take into consideration and we want to make visible for you as an engineer to evaluate when evaluating the part and evaluating the performance of your structural part. There are more things that we can take into account in the thermomechanical simulation. Things like recoater interaction, of course. See what the recoater does, where you may see issues with the recoater interacting with the part. But even things, and it's shown here on the lower hand picture, the part and powder interaction. We talk about the thermomechanical simulation, so it's not just the deformation that is interesting. When we see the laser operating on this part here, on the lower hand picture, we can actually look at how part of the laser energy is dissipating, zipping into the powder, the surrounding powder, and maybe causing effects like the powder sticking to a part or other things that we may or may not want to see at this point. Similarly, in a thermomechanical analysis, we can take into account more than one laser source. And that's what we're looking at here in this right-hand picture, where we have two lasers operating on the same geometry. First, they're working together, and we look closely now, you can see that those lasers are working at the different regions of the part, on the same part, and affecting or interacting with each other. And that too is something that absolutely requires a thermomechanical simulation. Maybe we want to be in a position where we want to optimize the temperature field, where we want to optimize the operation of the laser. There are techniques to operate lasers in such a way that we reduce residual stresses, and that of course requires us to be able to do such a simulation. One things that are related to thermomechanical simulation are failure simulations. What you see here is a validation of an experimental effect where we have the structure, which is a turbine blade that is being printed, and as you can see in the experiment, there's a crack developing between the support structure and the actual part. The crack develops during the print process. It's not something that is interesting for us afterwards, where we simply say, oh, it's red here, something could have cracked. What we see instead is the part cracking during the print process, and that in turn affects, of course, the heat treatment, not heat treatment, but the temperature distribution, because at this point, the support structures, which serve not only to support the part, to hold the part in place, but even to the thermal management, don't really do what they're supposed to do. Now, for some reason, this animation stopped and refuses to start. Okay, so it wants us to take the next slide. We talk about print to perform, and performance even affects the part after print process. We see here in this example is an in-service failure where the part cracks after the print process in service situation. And again, it is highly dependent on the existing residual stresses in the structure. On the right-hand side of this simulation, we can see a repair simulation. So the colors here represent the temperature field. Again, this is only possible in thermomechanical analysis. So we assume we have a part, a milling head or an aircraft part that has been damaged. We remove the part or part of the structure in a previous milling process, I cut it down to a base, and then we're adding new parts or new regions to the structure. And in this kind of process, it's interesting to see how the existing part, like the base part, so to say, is affected by by adding more to the parts or more to the structure to see whether it maybe deforms beyond acceptable limits. And that too is a highly temperature-driven process. Details can be revealed in the thermomechanical analysis. And again, we are looking at this turbine blade. And here we are looking at different types of support structures, maybe a lattice support structure, which has a great influence on the thermal management here, because the temperature, the heat kind of has to go through this maze of lattices. And what we can see here is we do represent them exactly with fine elements, not millions or hundreds of millions of tiny elements, which would take forever. With a reasonable number of elements, the simulation scales. Large computers can take, of course, more elements. And in thermal analysis and in the structural analysis, we're taking these detailed structures into account, allowing us to see what happens in detail here. Sensors and process control is a very important subject. And what we want to highlight at this point is many of the machines that you buy today, there are sensors incorporated that may affect and may provide feedback to the print process. In our simulation, we can monitor that. So in the same way as you're monitoring your real-world machine, we can monitor the process in our simulation, giving us information, and it's shown in this thermal radiation pattern on the bottom page here, is where things are happening, like what is the current temperature in the print, where maybe have thermal gradients which may affect the quality of the build, and for feedback and quality control, you can see whether all regions of the part have been heated sufficiently to give us the desired part quality. And we can actually use this sensor output in the simulation moving forward. So in the same way as the real-world machine can adapt its process to changing conditions in the build chamber, we can adjust our simulation the same way, allowing us to simulate the process beforehand to see what would happen if we change the laser power at a certain position of the part during the process, or maybe other things, to see whether we can improve the part quality during the build. And again, this is a highly temperature-dependent process, so that's why we do it thermomechanical analysis. On the micro level, we're looking at effects like melt pool behavior, prediction of unfused region, unfused powder, phase transformation, changing the material properties during the build process as a function of the process, temperature, time, and so on, grain size, and then things like the mechanical properties for the full-size part. And while we're not going into details at this point, I just want to show these slides showing that we can incorporate the process, and we've successfully been able to predict unfused powder regions. That's shown in this center image. We have a evaluated and validated framework for phase transformation simulation, which is part of the simulation that we offer. And we can use this information to predict mechanical properties from the micro model that's shown here onto large-scale full-size models. Now, when I'm talking about all things that we can do, here are some interesting examples, validation examples that are real-world parts that were run with our simulation framework. So yes, we can of course do simple analysis, cube-point double test simulations, like these ubiquitous cantilever bridges, and we have very, very good agreement between the deformation and the print simulation in these cases, of course. This is a very simple and commonly used structure, but as we learned, we are very good at predicting residual stresses, and here's an example of residual stress simulation done by a researcher called Wu, where the simulation and the experimental data have extremely good agreement, allowing us to actually use this kind of simulation in predictive mode to see what is happening and predict possible issues with the print. On the large scale simulation, we have the ability to simulate different processes, not only powder bed, metal powder bed processes, but even other processes like this full-size backhoe that was being printed. It's 2.5 meters in height in a deposition process, using the same technology, and again, thermomechanical analysis, and again on the small scale level, melt pool and microstructure predictions that were done on different materials, and again validated and proven efforts here. Talking about different processes, here are some other examples of processes beyond metal powder bed simulations. What we're seeing here is a simulation of fused deposition modeling, this kind of a shoe sole, and again we're activating the elements according to the path of the deposition tool that we have, and again this is a thermomechanical process, so we take into account that the material solidifies, maybe changes its properties during this process while this shoe sole is being printed. At Purdue University, they did a very interesting simulation of a fiber reinforced structure. And again, this was done with our simulation tools to simulate the printing of this duct tool. And in this thermomechanical process, the thermoplastic material was being deposited, allowed it to cure, and we're looking at the mechanical properties and things like crystallization over time, temperature management, and even things like fiber orientation, which is dictated by the print process and can be taken into account at this point. Hewlett-Packard's multi-jet fusion process is a very interesting process, I think. It's becoming surprisingly, or not surprisingly, increasingly popular with the car manufacturers and other people. And the interesting thing about this is that this kind of process was actually developed using simulation tools beforehand. So in order to validate and to create those machines, our customers were using software for that. Again, this is not your standard metal powder process. We can easily and with success simulate those processes thermomechanically again. Validation on small scale is shown here in the first image on the left-hand side from the Welding Institute, TWI, in Great Britain. We did a cooperation project talking about phase transformation and microstructure prediction that was presented at our Science on the Age of Experience conference. Very interesting presentation. Similarly, with the SimTech Institute in Singapore, we were able to show that we were able to predict in a predictive simulation, again, the stress distribution in a part, and this time it's a larger scale part, this X-shaped structure. So it's not only on the micromechanical level, but even on a larger scale level, where we're able to predict what is happening in the material, giving you the tool for predictive simulation. On the last of these three pictures here from KCNC, that's actually a very interesting thing what we're seeing, and it requires some explanation. It's a thin-walled tubular structure, maybe like air intake duct or something like that. And what happens when you try to print these structures, you may see a buckling-like deformation happening. That deformation is very hard to predict, and it's very hard to characterize. But the interesting thing, as we can see in this comparison between the blue light scan object and the simulation printed object, we are able to not only detect this kind of deformation, a defect in the part, we are able to predict that it is happening and where things like that are happening, which is again only possible in a thermomechanical simulation. A purely structural eigenstrain inherent strain type simulation will not show these predictions for large-scale deformation and this buckling type deformation. A lot of things that are validated, and I think in order to kind of combine and to have a summary of that, I'll hand over again to Anders, who will talk about the validation efforts in general.
Yeah, thank you, Stephen. It's well done to you for pressing all of that detail and not rushing it into that short span of time. It's something, obviously, if we wanted to talk about this, we could do a whole webinar only on the validation efforts. But our time is unfortunately not of infinite quantity, so we're still pretty happy with this and hope you've enjoyed what you've seen too. But as Stephen said, it makes sense to summarize a little bit. And if we try to do this using the headlines of process physics and materials, obviously the list of processes that you see should be a little bit longer. The reason why I'm saying this is because there are small differences or small nuances between different processes. But there is no way that we can possibly list everything that is going on, and some of these processes are even confidential, so we're not privy to what is being done. But as you can see, we have indeed done a lot of work to cover SLM, SLS, LTED, and so on, fused filament fabrication for that matter, all the way down to multi-jet fusion. And we're going to continue to do this for a lot more stuff. But I think personally, from a perspective of experimental mechanics, probably the most impressive features are the fact that we've been able to validate quantities such as temperature, distortion, microstructure, and I think above all mechanical properties alone, getting that link between what is being built as in the phases, how they ensue in the actual material, and linking that back to the mechanical properties is a feat on its own. On the material side, obviously, there is a lot of material work going on, and this list has certainly been expanded a bit, but it's still a good indicator for what is possible. So apart from the ever-present titanium, aluminium, various kinds of steel, and then also Inconel alloys on the metal side. Whereas on the polymer side, there's been investigations conducted both on polyether imide, so high performance, non-reinforced, in this case, crystalline plastics, ABS, that equals Lego to those of you who are interested, and then nylon 11 and nylon 12, which are usually cast grade plastics, but also finding good use in additive manufacturing, and of course carbon fiber reinforced plastics. So there's a lot going on, and I think one final aspect I want to bring up is, which you saw in Stephen's slides, is we're not just about the insular validation or the insular proof. We want to make this a full coverage solution going all the way from microscale up to macromolecular, all the way up to continuum scale, and so on and so forth. This would never be possible if we didn't have the simulation framework in place that we do, that allows you to conduct speedy, not directly detailed analyses for decision support in the very early stages of product development, but then once you get into the nitty-gritty details and you're actually planning to go onto the printer with your component, well, you want a little bit more assurance before you jam X thousands of dollars into basically a high temperature furnace with a laser pointer on it, that what's going to come out in the end is also going to be what your boss expected to see or what your corporation expected to see. And that is one of the strengths in this case, multi-physics and multi-scale. But instead of just listening to me go on and saying about, telling you about how great we are and how fantastic everything is that we do, just take an axe pick here. This is just a little sample of what you can expect in terms of validation efforts reading. If you want to check this out, then do take a snapshot or take out your mobile phones and go to the microsite, the dedicated microsite we have for additive manufacturing, which you can see on the lower right-hand side, and that will bring you straight to the place where you can pick up more of these. Now I need to close the loop a little bit, because we did initially mention shape compensation, and I'm very briefly going to explain what it is. This is super old technology. It's been in practical use since the 60s and 70s, but not perhaps in this fashion. But effectively what it does, it builds on the thermomechanical simulation. So the thermomechanical simulation gives you a vector field of deformations, which you then extract and use to compensate your part with something called digitized morphing. Then you compare the compensated part with the original part so you can see where the differences are, and then again go back and simulate the process on the compensated part and do a final comparison to see, is the as-designed component going to look like the as-built component? That is the strength of this tiny little piece of the puzzle. So if we want to summarize here, I can take one little final excursion, because we hope we've more or less unfolded the extent of our thermomechanical solution capabilities. And effectively what I just want to say is that our strategy is truly a full coverage digital thread which is native throughout the 3D Experience platform. We've not talked about the platform at length because it's more or less self-evident in this case that it is the foundation for proper collaborative work. So if you want to picture the additive manufacturing solution in kind of a subway network, this is it's actually not a bad analogy, because there are many ways through which you can go from input to final component in the end, but you're not limited to one line. There are many different extensions you can take and many different routes and many different inputs, so various places to start your journey. And above all, there is learning content for all of this. It's basically when you put all this technology together that we have, we bring it together through the individual applications that are model-based, data-driven, above all backed by science. And it's all to enable you guys to make parts that work in the end and have your boss be happy with what you do. Of course, everybody wants that. It's good for the yearly bonus. Now, if you want even more details, there are two places. Like I just mentioned, there is the Additive Manufacturing microsite, dedicated place to go. So that's the centralized, the central portion QR code, if you want to go there. But for those of you who don't really find the time to sit down and read, or simply, well, you're a little bit on the go all the time, then why not check out our YouTube channel, 3DS SIMULIA, and with the specific focus on a learning section on additive manufacturing, which we are producing and where content is being produced all the time and kept up to date, and that is the bottom right-hand QR code. This is actually the conclusion of today's webinar. I'm going to leave the slide up so you can continue to take snapshots and do whatever you want. But on behalf of Stephen and myself, it's been an absolute pleasure talking to you guys again today about a really, really interesting topic. And now what we're going to do is to address your questions as best we can and hope for a very, very nice Q&A discussion. Thank you very much for your attention.